There are many ways to solve physics problems. We have certainly used algebra, we've used geometry, and we've also used graphing. For the rest of this chapter, we're going to focus on the power of graphing to solve problems. A position time graph has position on the y-axis here, that's x, and time on the x-axis. Notice how both axes have been labeled along with units. Now we can certainly graph the position at any time. However, we can also use this graph to find an object's velocity. So just to review dependent and independent variables, the x-axis, which is time, is the independent variable, and the y-axis, which in this case is x, funny enough, is the dependent variable. Here are the steps you need to create a position versus time graph. First, we're going to use a Cartesian coordinate system. Basically just has the axes at right angles to each other. And so we'll draw the vertical and horizontal axis. The vertical axis will be position, which is labeled as x, and the horizontal axis will be time. Make sure you add the units, meters here, seconds here. And now we'll be adding points to the graph. But to add these points, we need to know both the position of the object and what time it happened, what time it was at that certain position. We can also create a velocity time graph. However, in this case, time will still be the independent variable on the x-axis, but we're going to plot velocity in terms of meters per second on the y-axis. Now, this clearly will show an object's velocity at any time. However, by using a couple math tricks, we can also find its displacement and acceleration, and we'll get to that in the next few slides. So let's get going on graphing. We are going to start an object at a position of x0 equals 4 meters, and we're traveling at a constant velocity of 2 meters per second for 6 seconds. And we want to find where we are at various times. Well, let's see what this tells us. What does constant velocity mean? Well, that means that acceleration, which is the change in velocity over time, is equal to 0. So let's look at the equation we're going to use to find position. It's x equals x0 plus v0t plus 1/2 at squared. Okay, there's no acceleration for this problem, so this term gets wiped out. So to find a position at any future time, we just need the original position, which in this case is 4 meters, plus the initial velocity, which is 2 meters per second. And not only is it the initial velocity, it's a velocity at any point, and then we'll multiply that by time. Okay, that's not the best t, but that represents time. So let's just look at the first one. Your position at time 0 is going to be 4, and that's exactly what they told us. So let's see what your position at 2 seconds. Well, it would be 4 plus 2 times 2, which is 8 meters. So there you go. At time 2, you're at 8 meters. And notice the subscripts here. These relate to the different coordinates we have. So at time 5 seconds, it would be 4 plus 2 times 5, that's 14 meters. And at 6 seconds, it would be 4 plus 2 times 6, which is 16 meters. Another way to handle these subscripts, instead of putting 1, 2, 3, 4, because there were 4 points, you could use the seconds. So this could be x0, this could be x sub 2, this could be x sub 5, and this could be x sub 6. Physics is very flexible. For this problem, we will start at x0 equals 4 meters, and we'll travel at a constant velocity of 1 meter per second. So constant velocity implies that the acceleration is 0. And we want to draw a position versus time graph. Well, here's the equation. X is equal to x0 plus v0t plus 1/2 at squared, but we know acceleration is 0, so we'll just leave that term out. So let's see if we can move these points. At x0, time 0, we're at position 4. So let's take this guy here and put him up to position 4. At time 1, that would be 4 plus 1 times 1, that's 5. So at 1 second, we were up at 5 meters. There we go. Time 2, 6 meters. Time 3, 7 meters. Looks to be a straight line, pretty good. Time 4, 4 times initial velocity of 1 is 4, plus 4 is 8. So time 4, we go to 8. And likewise, time 5 will be at 9. So there, we've dragged and dropped the positions. That looks to be a straight line. Let's see if we can draw an arrow here and show that. That's pretty good. Oh, can move the line down a bit, but you get the idea there. We have a straight line graph for the position versus time. Now let's work on a velocity versus time graph. And in this case, we're starting in a position of 4 meters, and we travel at a constant velocity of 2 meters per second for 6 seconds. So let's draw the velocity versus time graph for that. This one's pretty straightforward. They tell us that the velocity is 2 meters per second constant no matter where we are. So at 0 we're there, and hang on, at 1 second we're at 2 meters per second, at 3 we're at 1 meter per second, so on and so forth. So at every point the y value or the velocity value is always going to be 2 meters per second. So when we draw a line of best fit through that, okay, that's what it looks like. And let's check the answer. And there we go. It is exactly constant. It stays 2 meters per second the whole time. Let's draw another position time graph, but we're going to change it up just a little bit. In this case, we're going to have a negative velocity. It's still going to be constant, so I can still just use part of the second kinematics equation. X is x0 plus v0t plus 1/2 at squared, but a is equal to 0, so we're just left with this. So let's see where we put the points. At time 0, well, it tells us x0 is at 10. Okay, and at time 1, we will have 10 minus 1 times 1, or 9. So at time 1, we have 9. Time 2, we're at position 8. Time 3, position 7. So you can see what's going on here. Our position is getting closer to the origin. Why? Because we're moving in the left direction. So if we started at x equals 10, we're going to move closer and closer to the origin. And let's just do a line of best fit there. And that will continue on like that. And we'll pull out the answer key, and that's exactly what we did. We are now in a position to analyze position versus time graphs. Earlier, we talked about how slope was used to analyze motion. The slope in a position versus time graph, which is what this is, you have position here and you have time here. The slope is equal to the position change divided by delta t, and another name for that is velocity. Therefore, slope is equal to velocity on a position versus time graph. Here are 3 examples. In this first position versus time graph, we have a line which has a positive slope. That means that the velocity is greater than 0. Here we have a negative slope. Hopefully this is familiar to you from your algebra class. We have a negative slope, so the velocity of this object is less than 0. You started out at one position, let's say this is 10, then you go 9, 8, 7, 6, you're getting closer to the origin. So that means you're moving to the left. That means you have a velocity to the left. And if you have a zero slope, which is a horizontal line, your velocity doesn't change. It stays fixed. So you are not moving at all there.